Yes, hello guys. And now I have to discuss about, we are discussing definite integral, okay? And the properties we have discussed about, then function as a limit of a sum, definite integral as a limit of sum, that also we have discussed about. And then we discussed about, okay, integration of a, series, integration as a limit of a series. Okay. Then, now we have discussed about the properties, further properties, the same property, we are to interpret them geometrically, with geometrical interpretation of the property. Today I am discussing about. Alright. So that is the point. Now all these properties which are written down here, mostly students are asking. Now are written or we just reply them. For them, this is the discussion further I have taken here. Okay. This is further that definite property of definite figures, further discussion or geometrical discussion, or we may say geometrical interpretation of those properties. Okay, so that is the base topic. Now let me take these properties one by one. Now first property says that if fx is greater or equal to 0 for all values of x in the interval, in the closed interval AB, where f lies between A and B, then a to b fx dx is greater or equal to 0 is positive. That we have discussed. Now as a limit of sum, this is very simple to describe. That as a limit of a sum, we discussed about that when we find out the area of a curve, that area is always positive. Okay, so and that area was limits a to b fx dx. That was limited by this. Okay, and which was equal to limit h into h tends to 0, okay, or n tends to infinity, h into within bracket fa plus h equal up to fa plus n minus 1 into h. So that we put there as a limit of sum. Now this is equal to a to b fx dx. Now the first very theorem or very property, it is self-proof because area is always positive, it's not negative. So we cannot say that this is negative, okay, but this is the check for the definite integral, whether the definite integral is negative or positive. But in this case, it's positive because it represents an area of the function, okay, of the curve. In this case, the curve, suppose fx is the curve, then the area of the curve from the limit of a sum, okay, or definitely as a limit of sum. There we know that area cannot be negative, it is always positive. So this is self-proof. Let me take the first question. Now question number 1 here, what it says? It says that if fx is greater or equal to 0, okay, for all values of x, where a is less or equal to x is less or equal to b, okay, for all values of x, then we have to prove that a to b fx dx is greater or equal to 0. This is greater or equal to 0 or positive. That we have to discuss. So now this is, as I have just described, that by the definition, let me proof here. This is proof here. Okay. Proof here from the definition. Let me write here. From the definition of the definite integral as the limit of the sum. Okay. As the limit of the sum. As the limit of the sum. Of the sum. We know that this a to b fx dx is equal to, we know that this limit x tends to 0 or n tends to infinity, bracket for fa plus h plus and so on up to fa plus n minus 1 into h. This was into h. This was your definition of this function as a limit of the sum. This is positive, so this represents an area. This area is always positive, which is always positive. Now it represents, okay, it represents the area of the curve fx. And if I describe it geometrically, as we were discussing about, this is the curve y equal to fx. This is y equals fx here. Now this curve represents, if I take here a, that's s equal to a here, and this is s equal to b. Okay, so within the limits a to b, we have this area which I described as, okay, which I already described this. This is infinity. If I take this infinity, this is a here, this is a plus h, this is a plus 2h, a plus 3h, etc. And finally, last one is this one with the x equal to b here, where b is a plus n. Okay, or a plus n into h. This is a plus n into h, and this last one is a plus n minus 1 into h, and this is a plus nh. B a plus nh, n into h. Last one. Now this area which is represented by limit a to b, limits a to b, for this whole area where h and when h and 0, h is then limited, then we divide between this area between a and b, the ordinates a and b, in infinite number of terms where n tends to, if n tends to infinity, then h is 0. This whole value h is 0. This whole will be represented b minus a. So finally b minus a. So this is what we call limit. This is positive here, for this represents the area of the function as a limit of the sum. So this is positive. So as area of a limit, or as the that here, the area of the curve between the curve and the x-axis and these two ordinates, between the curve x-axis and the two ordinates, x equal to a and x equal to b is positive, is greater than 0. What is greater than 0? 0 is when this area is, this point is this, coinciding with x-axis, then this area will become 0. It can be 0, but it is positive in this case. If fx is positive given to us, and fx is greater equal to 0, when it is greater equal to 0, this function is positive. Curve is positive here. It will represent the area between x-axis and this curve will be positive always. Okay, this area is positive. Because of that, this function is positive. This implies that limit a to b fx dx is positive. If fx is positive, this is okay. Now this fx, this limit, definite integral, it will be fx dx may be positive. If it is negative or positive, this we have to check. This works as a check for the definite integral, whether the definite integral given to us is positive or negative. But in this case, positive, because it represents as a limit, as a definite integral as the limit of the sum is positive always. This is positive. This is question number first we have discussed about. Let me talk about my second question. Second thought, geometrically or interpretation of this, how we will interpret that is discussed about. Let me talk about the second thought, second property, here. For the second property, it says that if fx is second property here, it says if fx is greater or equal to gx. Okay, the two functions are given to us, and both functions are integrable. Okay, and they are integrable, and both are integrable, in AB, between AB. Then we have to prove that limit a to b fx dx is greater or equal to limit a to b gx dx. Okay, so this we have to prove here. Fx, the definite integral a to b fx dx is greater or equal to gx. If it is given to that fx is greater than or equal to gx. If it is given, then we have. So from the first property, we have just proved that this is positive and this is also positive. This we can prove because this also present the area, this also present the definitely as lambda equals this is positive in itself positive. Whatever relationship is given between them, that will be maintained further option after given definite integral. Definite integral also the same relationship will maintain or will be maintained. That relationship cannot be neglected if it is given towards whatever. Because this definite integral as a limit of this one is positive, this is also positive. And they are given that this is positive. And if I take, let me take, if fx, okay, a function fx is equal to, let me take, fx minus, okay, suppose this function is given. Now if I find out, this implies limit a to b, then this function fx is integrable in a, and here fx have taken is integrable in the limit a to b, or between these two limits a to b. Okay, this is integral, or fx is that integral, it's an integrable function. If this is positive, you know that if it is integral in this interval AB, that means this is definite integral. That integral is positive in this case. From this is positive, we will give from the question number 1, from the property 1. In this case, property 1. The property 1 in question number 1, or let me take in question number 1. In question in property, the property in question number 1 that we have just discussed about. Question number 1. What is given to us? That if fx is integrable in AB, that is given to us that x is in the okay for all values of x in the interval is positive in this interval a to b, then this is positive. This is given to us. This implies that if it is positive, then these two are also positive. This implies that limits a to b fx dx, let me apply to this, minus a to b gx dx, they are also positive. Let me take the first equation. Okay, this is dx dx. So these two are positive from this first one, but we have assumed that this is equal to this. And if I take second, the second, okay, they are integrable because fx gx both are integrable in AB. Fx is also integrable. We have taken that fx is equal to, and this is small fx minus dx. Now if fx is positive for this integral in the interval AB, from the first question number first, that a to b fx dx is definitely like the limit of the sum is positive because it represents an area. The whole area is positive area of any curve between curve and the x-axis and the two ordinates, and it is positive here. Now it is positive. It means we have applied this positive sign to this and this also. The two limits a to b we have to apply to these two also. This must also be greater than 0. If this is greater than 0, it must also be greater than 0 equal to. It means this implies that this must be greater than this because the difference of these two is positive. That means this is greater than this. It implies that a to b fx dx is greater than a to b gx dx. This we have written now. So any functions which are integrable in a given interval, and if there is a relation between them that first function is greater or equal to second function, then integration of them in the same interval will maintain the same same vertical property or same relationship, positiveness or positive. They will be still positive. If the difference is positive here, this is greater than this one. This is implied here. Okay, so the same relationship will be maintained if the functions given are integrable in the given interval. Okay, that the second question is here. So this is how properties can be geometrically we can Okay, describe them. Suppose there are two curves here. Suppose this is the first curve. Okay, this is gx here. Let me take this gx. Y equal to gx here. And this is second curve. This is y equal to fx here. Now the area under this curve and this curve, if I take the same origin in A and B, okay, this is A and B. This is x equal to A, and this is x equal to B here. Between A and B, we see here that Gx is a smaller area, okay, or area below Gx and between x-axis, ordinates x A and B is smaller than area between this. So we see from this that limit A to B fx dx is greater than gx dx. From this geometrical integration also we can prove that if this is given to us that this is greater than this, then the area under those curves and between the x-axis and the two ordinates will still be greater than the second one. I mean, this is number one. This is what we can geometrically prove. Origin is y-axis, x-axis, this, y-axis. In this way, geometrically also we can prove this area in A to B of Gx is smaller than that of area under fx function. This is our second question. Now let me talk about third question. Third property. What is property number third? Let me discuss it. Now property third says that if fx is continuous in closed interval AB and the small n, any constant number is greater, is smaller than fx is less than n, means fx is lying between m and n. Okay, the function is where n and n are constants, then n into b minus a is less or equal to a to b fx dx is less or equal to n into b minus. Now if I look at geometrical interpretation of this, if I do geometrically, then it's very simple. Let me take it geometrically. Question for the third year, it says if fx, okay, is continuous in closed interval AB, okay, function is continuous closed interval AB and small n is less or equal to fx function is less or equal to, means this function fx is capital N, you have capital N less or equal to capital N. So fx function is continuous between the two intervals m to n, and this interval like a to b, this is m to n capital N. Okay, so this function is continuous in this given interval m to n that is given to us. A and b is also given to us. Okay, so now let me take that what are these functions here. Now if I take that b minus a, b minus a limits, the limits given to us. Now if I find out, let me prove it geometrically. Now we know that what is b minus b, okay, from if I take m small m and capital M, that is given to us. Okay, now if I multiply this by delta xi, for delta xi represents the area between the curves. Suppose this is fx function here, so this is y equal to fx, y equal to fx, the function given to us. Okay, and if I take, let me take this function in this case, not like this, we take this function as, okay, and this area, and here if I take, okay, let me take it. Okay, now this is up to this point. If I take, let me take this area, and this is the curve here. The second area is this, and if I take that in dotted form, okay, and this is the two areas. Here, this distance is small n because this is constant value, and this is capital N from this point to this point, this is x-axis here, y-axis, y-axis, x-axis. Geometrically left, I am proving this. Okay, so this is the function y equal to fx given to us. This is the curve. Okay, now this curve is here, line between. Okay, and here we see the small m, this m value is smaller than this m capital M here. Okay, now if I take this value that m small m okay is greater than this one. Now what is the area under this curve? You know that if I find out area of this curve, okay, line between these two and dividing this into n, okay, n parts, like this is small h, this distance is small h, okay, this is h plus a, okay, and this is small a bar here is capital responsible a, this is up to this is b, this is x equal to a here, and this is x equal to b, same interval. But this length up to this point is this, but this is up to this b, and this is a here. Okay. So b minus a, it was given to us, look at this, n into h bars, or here h bar equal to b minus a upon n, is v1 way, or nh equal to b minus a. Right? So nh bar equal to b minus a. Now this difference b minus a, this ns value is when h tends to 0, or when m tends to the h tends to 0. And this b minus a, that value will be, I mean, if it is 10 to 0, so 0, then b equal to a, we just choose it. But in this case, b is greater than a, because this b, I mean, the area between this b to a, or these two ordinates, that area are given to us, that is b minus a right there. Now this, we are given here, that is, if I prove this, that n into b minus a, small b minus a, is less or equal to, because function fx is continuous in the interval if it is given to us. Here, fx is continuous function in the interval, in interval ab. So what our a, this is closed interval, closed interval, because x line between a and b, but greater or equal to 1. A and b can also be the value of the function here. Now let me take, so here fx is continuous. What does it mean? We have just proved that n into small n, if I take, they are given to me, small n is less or equal to fx, or it is, if I take with fx less or equal to capital N, and delta xi, let me take, this is delta xi here, where I equal to I function. This is also delta xi, fxi, delta xi, and this is n delta xi. Okay. From the definite as the limit of the sum is here proved that this area, let me write it properly. From the definite integral as the limit of the sum, definite integral as the limit of the sum, as the limit of the sum, we have proved that, okay, suppose this is small m here, we have taken this small m, in this case small m is given. If I take m delta xr, if I multiply by delta xi, it is less or equal to fx I into delta xi less or equal to n delta xi capital N. This is capital N because smaller n is less or equal to capital N that we have taken from this graph here. This is smaller n up to this only. This is, let me take points here A, this is B here, this is C, let me take this point here, C, M is here, and this is D here, this is E, A, B, C, D, and let me take here these points, here this point, and this point, and this curve point. Curve point, let me take B, C, D, E here, this is F, this is G, and this is H. So we see from here that area. Now this is from definitely as a limit of some by delta xi. Delta xi will represent when limit h tends to 0. Okay, when limit h tends to 0 or n tends to infinity, n tends to infinity. Okay, this is fxi into delta xi into delta xi. Here fxi will represent as, let me take h into delta xi. Delta xi will represent b minus a. It will be b minus a here. It will be delta xi here. Okay, if I take this delta xi into fxi, the function given to us. In that situation, this will be positive, so this is definitely the limit of it. That means n into as the limit of the sum delta xi is less or equal to fxi into delta xi less or equal to capital N into delta xi. Alright. Now if I put as the limit of the sum, you know that delta xi is equal to how much? Delta xi finally sigma sin I is equal to 1 to n delta xi when I tends to this and limit h tends to 0 will be equal to, we see here this, what is this whole value will be, we take x1 minus a is the starting point here, and x1 point, x2, x3 and so on. x1 minus a, so this is x2 minus x1 plus x3 minus x4, sorry this is x3 minus x2 and so on. And the last one is here xn minus 1, xn minus 1 minus b here. Okay, so this will give us b minus a, or I'm sorry, this will be b minus x minus 1, b minus x n minus 1. All x will be cancelled out, only this value will give us this limit, and I limit sigma sin representation, sigma sin I is equal to 1 to 1, and the limit n tends to infinity. Put here limit n tends to infinity also. This will give us b minus a. Which means delta xi when limit I equal to 1 to n tends to infinity, delta xi will be finally b minus a. This will be b minus a. x1 cancelled out, x2 cancelled out, and so on, and up to xn minus 1, and this will be give us b minus a. In place of delta xi, if I put b minus a, that will be there. So let me put it here. So this will be n into b minus a for delta xi and limit then I equal to 1 to 1. Okay, and limit n tends to infinity. In that limiting position, this delta xi value will be b minus a. That's all equal to fxi into b minus a. So this is nothing but the a to b. This is fx into dx. This value is fx dx. This is less or equal to capital N into b minus a. Okay, this is from definite here as the limit of the sum. This we have put here that b minus a, which is delta xi, with this here, and this is the limit as this one. Okay, so this area of this curve is lying between these two values. Now, if I prove it geometrically, okay, this has been proved. Now, if I take it from geometrical, this figure, take geometrical definition, what is here? Now we see here But this m into delta xi is this whole value. This is b minus a area of this curve. Now we see from the geometry, geometrically from figure we have area ABCD is smaller than equal to, we are taking y because it can be, if this curve takes the value of it coincides with the line DC, then the two areas will be equal. So it will fx side area ABEF, or line between the curve and the axis, area of the curve, area under the curve, area under the curve, y equal to fx. It is less or equal to this area ABGH, area ABGH, this whole area ABGH, and this area under the curve is ABEF. I have taken this area under the curve, that is sufficient. Okay. What is area ABCD here? This is small n height and length is b minus a. Okay, so this is nothing but small n into b minus a is less or equal to. Now area under the curve is limit a to b, nothing but fx into dx is less or equal to. Now this is n, height is n, that is n. Okay, and this breadth is b minus a. Geometrically also, geometrically we have proved now that this value is given to us as, okay, this one. So this is how we can prove geometrically also. So this is question number third one here. So this is property which we have explained geometrically as the best limit as a definitely like the limit of the sum. So from there also we could get this same definition. Now the fourth question, which is very important. Let me discuss about that also. Now property number 4. What did it say? Let me take fourth property also. Okay, now property number 4. What is fourth property says? Property number 4 is if gx is positive and small